Hey, welcome back to Fat Mama Physics. In these videos, we are going to talk about impulse. Mostly we'll be focusing on examples, but let me do a quick run through of what I need you to know about impulse before starting these examples. First of all, when we talk about impulse, we get to answer so many interesting questions, such as, why do we wear seatbelts? Why do we have the crumple zones in front of the car? That's the part of the car where if it goes through a crash, the front of the car kind of just encases in or just gets buckled in without having the whole car, kind of the framework getting destroyed. We can also answer questions such as this cool video that I found. And no, I don't do parkour. I wish I could. But let's take a look at the parkour rule very quickly.
Rolling. The most important and fundamental move you will learn in your parkour and free-running journey.
So did you see that? This is the time where I have to say, please do not do this at home. Okay, I did not show you this video for that. I showed you purely for the reason of educational purposes. But I do want to show you why it is really interesting how this person is able to go down this very high building, going through a parkour roll without sustaining any sort of injuries, of course, with lots of practice and probably direction. So then, why doesn't get hurt, okay? And that's what these lessons are going to help you get through and answer these questions. So let's get down to impulse. In the last video, we talked about what change in momentum was. And that was the final momentum minus the initial momentum. If the mass of your object doesn't change, then this we can simply write as mass times the change in velocity. In fact, we call this change in momentum, we have a specific name for this change in momentum. We call it impulse. Very impulsive, I say. And impulse, we can also write this as change in momentum here, but we also found out that impulse has something to do with a force that needed to either get an object to stop or to accelerate an object, thereby having this change in velocity here. So it's related to force in some way. To find this relationship, and I'm going to write an equal sign here, we're going to need something on this other side of the equation. Hint, hint, it's going to have force in it. And to find this out, we need to look at Newton's second law, which is F net is equal to ma. So let's find out how this relates by saying that, okay, well, there is no acceleration in the above term, but we do know acceleration is the final velocity minus the initial velocity divided by time, or change in velocity over time. What we can do now is to substitute that back into our F net equation and see what we get. And this F, I'm just going to write it as F. It can be a net force or it can be an average force acting on an object. I am going to have mass times change in velocity divided by time here. Okay? Ooh, isn't that starting to look like something now? Now, we also know that this term on the top is change in momentum. Aha, all over time. So now we see that F net, the Newton's second law, takes on a new form in which we can talk about Newton's second law in terms of momentum. To be more specific, this is, in terms of momentum, we say that the rate of change of momentum is directly proportional to the force acting on the body. What the rate of change is how much momentum changes per unit of time. In fact, when Newton first came up with his second law, he didn't actually write it in terms of acceleration like how we learned Newton's second law. He wrote it in terms of momentum. Whenever you are asked for Newton's second law in a paper or a quiz or an exam, most of the time you will refer to this top definition I have here, unless the question specifically asks you to write it in terms of momentum, you would write whatever I have that is over here. And this also emphasizes the fact that what we are learning in this unit is essentially Newton's three laws. When we talked about momentum, that was very similar to Newton's first law of inertia. Then today is Newton's second law. What's coming up next? No surprise there. But that's going to be in the next future lessons. Coming back to today's lesson, we haven't finished this part yet. We know impulses change in momentum, and if we want to solve for momentum here, change in momentum here, we need to move the time to the other side, juicy time, okay? So then we get force times time is equal to the change in momentum, and we call that impulse. So here on the other side, we have the force times the time. Actually, that should be delta t. And this force can either be a net force, usually it's the force causing your object to accelerate, so some sort of average force that's applied to an object. Of course, sometimes the force changes, which we'll deal with later, which then also gives us another way to express momentum or change momentum, and that's Newton's times second, exactly F times t. Whenever you are asked in a question to calculate impulse, remember you can calculate using change in momentum, which is m times delta v. But if you're not given those values in the question, you can always check if you're given the amount of force applied to an object over a period of time, which then ft also helps you to calculate impulse. For example, example number 1, here I have an example which a 0.5 kilogram water balloon is thrown against a wall 32 meters per second and it comes to a stop. Oh, it's giving us the times it stops in 0.73 seconds. Calculate the average force the wall applies to the water balloon. So if I had to, this question doesn't ask you for impulse, but let's say this question asked you for the impulse. The impulse you would get from the change momentum. Since you're not given the force, though you are given the time, you're not given the force to calculate impulse, okay? But let's actually do this question properly. You have a mass given to us from the water balloon. It was going at 32 meters per second, so that's our final velocity. Sorry, that's our initial velocity. It comes to a stop, that's our final velocity, and we're given the time, and we want to find the average force. So then we're going to go to our impulse equation, delta p equals to F, and then since it's an average force, I put F average times delta t, and we want to find the average force, so we're going to divide both sides by our time, to give us the force average is equal to the change in momentum over the change in time. So then the top becomes mass times final velocity minus initial velocity divided by the time, since that's the change in momentum, is a change in velocity there. And then the mass we have 0.5 kilograms, and the final velocity is 0. The initial velocity is 32 meters per second. All of that divided by the time, 0.73 seconds. Putting all of that in our calculator, we get negative 21.917. And we're going to round that to 2 sig figs, which is going to be negative 22 newtons. So what does that mean is that imagine we have a wall, we have a water balloon that is coming in, and it splashes everywhere, it comes to a stop. In order to stop that balloon from going through the wall had to apply a force in the opposite direction of negative 22 newtons for 0.73 seconds in order for it to do that. Okay, so this is what this equation looks like when we're doing these kind of questions. And what I should have done earlier was talk about direction, so that was my fault. Although, you've seen this question before, have you? And you've also seen this question down here before as well. And you got it. This is the question I'm going to get you to try before I go over it. So, good time to pause the video right now and try this problem. Now, I'm going to do this question on Fast Play. First off, we have the mass of the bouncing ball as 0.5 kilograms, and the ball is thrown against a wall with 32 meters per second, so we're going to label that as the positive direction. It bounces back with the same speed, but it's in a negative direction, so I'm going to put a negative in front of the 32 meters per second. Using the impulse equation and solving for the average force, we're going to have to divide both sides by t. We're left with change in momentum over the time. We substitute in the mass, we substitute in the velocities, don't forget the negative signs in there, and the time that was in contact with the wall was 0.1 seconds. We get a total of negative 320 newtons. And here we have the solutions for example 2. So a couple of things is that when the ball bounces back, notice that I have to include a negative sign because it's opposite in direction to how the ball was bouncing towards the wall. So as a result, we get a larger change in momentum, or a larger impulse for that matter, just like what we did previously, but now with the time. And notice something. Notice that this time the ball was in contact with the wall for a shorter amount of time, with a larger change with a larger force needed to apply to the ball for that to happen. You might be thinking, well, we had a larger change in momentum. That's just not fair. But let's say we are talking about the same bouncy ball and it was in contact with a wall for a longer period of time with the same change in momentum. Let's see what would happen as a result there. Okay, so instead of dividing by 0.10, I'm going to divide by 0.73, which is exactly the amount of time we used in the previous question. And notice we get a much smaller force needed because the force has more time to act on the bouncy ball to get it to change direction. Okay, so we're going to talk more about this later and how that relates to all the stuff I've been talking in the beginning of the video. The purpose of these examples was for you to get used to this new equation. And going back to this example, we got negative 320 newtons, in which the wall had to apply in the opposite direction to not only stop the bouncy ball from going through the wall, but enough to also get the ball to bounce back in that short amount of time. So I thank you for watching this video. I hope you learned something, and good luck on your questions problem solving. Fat Mama's Physics signing out.